All right, we have Dave here, who is the maker of practical flow meters, and he's going to talk about the differences between two meters. This is the which
Thermal mass flow meter and a vortex flow meter. So thermal mass flow meters were started many moons ago by Sierra Instruments in Carmel Valley by John Olin and Jerry Kurz, and they've advanced significantly over the years. And they really enjoyed a large segment of the industry because they could measure extraordinarily low flows. So when these came out, they were all analog devices. Now they're digital devices. The microprocessor that's in here costs a nickel, runs at 280 megahertz, can do magical things that were unheard of when we made these things in the analog world. As well, the vortex meter has enjoyed similar advances in electronics. The vortex meter Achilles heel is vibration. The thermal mass flow meter's Achilles heel is temperature. This thing doesn't really like things to change or gas composition. Temperature can be compensated, but typically most of the companies who make these don't do it properly. The way this thing works is it looks at the energy taken away by a cylinder and cross flow, which is described by King's law, and King's law is much more complex than we see in the textbooks. King's law involves Prandtl number, Nusselt number, density, viscosity, every crazy thing.
But just to back up on the King's law, so basically what happens is the more flow is going through here, the more temperature is lost?
Yes, energy is drawn from the heated sensor, and in one way of running these, we could run a constant temperature difference. That's what we do. You could run a constant power. That's what other
So you
folks
measure the
do.
temperature difference between, say, here and here?
Yes, the little one is the temperature recorder, and the large one is
I'm going to zoom in here so we can
Yeah.
see what we're talking about. So we have two different
the little sensor, temperature sensor, large one, velocity sensor.
and we're measuring the temperature gradient between that, and the more the gradient, the faster the flow is.
That's right.
Essentially.
Yeah, that's it in a nutshell.
And as David said, it sounds simple, but
Yeah, so there's a lot of ways to do this wrong and a few ways to do it right. Mostly the industry tolerates it's done fairly well. So with the advances of a microprocessor, we can describe all of the heat transfer and fluid mechanics, everything about this in full-blown 64-bit floating math and describe it. This one, as a vortex meter, it's a time domain machine. There's a bluff body in front of the flow meter. Behind it is a little piezo transducer. There could be many different methods of measuring the vortex shedding frequency.
So maybe let's talk about a vortex. Essentially, if you have a river and you have a rock in the river, you're going to have this crazy stuff happening behind. Or if you think about an airplane wing or something, in a wind tunnel, you have this crazy stuff.
Yeah.
So that's what we're measuring here, is we have something blocking the flow, and then it's creating all this vortexes, and we have a piezo crystal measuring that vortex.
That's right.
correct. Cool.
And also think of a flag. If the flagpole was infinitely small, the flag would not wiggle. The flag is only wiggling because the bluff body, the pole in front of it, is causing a disturbance. So the flag is reporting the velocity by the speed at which it's wiggling back and forth. So imagine, just think the funny part about a flag. If it was infinitely thin, the flag wouldn't wiggle. If the bluff body was infinitely thin, this thing wouldn't work. So we have to create a certain
width of the bluff body.
Yes, and there's a magical width to diameter, all this, there's magic to it, just like there is, in anything, there's magic.
I don't want to gloss over that, but it sounds like you spent a lot of time and effort figuring out the right size of this bluff body, and figuring out which creates the best. Okay, cool.
And because the enemy of this, Achilles heel, is vibration, because it's a piezo crystal that's sensing that vibration, wouldn't it be
So hold on, so you can have vibration caused by the
by a pump hooked to this that's vibrating at 3450 RPM, blah, 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 and this thing's vibrating at 100 hertz, and it's that 3450 is impressed on top of the 100 hertz, causing a complex waveform that we discriminate using digital signal processing to filter out those high frequencies. And we know the frequency range of this, 100 to.
So if something's 100 kilohertz or something like that, you're going to filter it
Yeah,
out.
we filter it out.
You know the frequency ranges that the piezo crystal is going to vibrate if it's
Yeah.
liquid that's flowing
Yeah.
through it.
There's another way. Imagine having,
Actually, I want to just back up on this because to me that sounds pretty incredible that you're getting turbulence
yeah,
and that's causing the piezo crystal to vibrate, and
That's
the
right.
piezo crystal is picking that up and figuring out how much water is flowing through. Like, I know you live this, but to
Yeah.
me that's pretty incredible.
how much water or gas. This machine can work for water, gas, wet gas, hot gas, cold gas, steam.
Anything that creates turbulence, essentially.
Yeah, anything you can run through it. It's an amazing machine. It's approaching what this can do. It's becoming, with new electronics, quite the competitor to this one. This one is extraordinary at really, really low flows. And those are important to people. But if it's not, there's no sense in it.
Because you have to get turbulence, and you're not going to
Yeah.
get a lot of turbulence with a low flow.
Yeah. Yeah, that's right.
So the benefits, I guess this works extraordinarily good for all applications where you don't have something else creating vibrations.
Yeah, and if there is vibration, we would have the ability to extract that spurious signal.
Try to figure out what the vibration is, just
We
like
can do
noise
it.
canceling
Yeah,
headphones or anything
that's
like
right. The other thing is we could sense that vibration using a heat sensor, a thermal system that measures the pulses that go back and forth that actually creates a wake that cools or that creates a velocity behind that we measure with a thermal sensor that wouldn't care about vibration. So there's ways to do it. You have many different ways. Folks have done this with pressure. Some people have done it with density. Some people have done it in fluid mechanics using the change in the electromagnetic lines of flux. So you can actually make a vortex meter with a mag meter, electromagnetic sensors, and it has no sensitivity to vibration.
Oh wow.
So this has a lot of potential to keep getting better, and
So this is the wave of the future,
Yeah.
basically, because the error is something that we can figure out ways to subtract out.
Yeah.
Whereas maybe the error here is harder to subtract out. Is that a fair?
yeah, a little harder because you have to tell this what the composition of the gas is, and there are ways to do that. In another meter we have this meter.
Hold on, let's back up on that one because different gases have different heat conductivity.
Have all the different properties: density, viscosity, thermal conductivity.
So you have to calibrate it based on your material.
Yeah.
And if your material is, I guess the material is usually what they say it is, but maybe not all the time, eh?
No, it isn't always.
So that's the problem is we think it's
Yeah.
one thing with one heat conductivity.
Yeah.
Reality, we have the wrong heat
So,
conductivity.
so
we're
for
screwed.
people in natural gas, they'll buy these and they'll tell you how much methane, how much CO, and they'll tell you a list of 7 gases for biogas to make this thing work. And the folks who make these, I know because I do consulting with them,
Yeah.
don't really do it the perfect way, let's just say, but
Mhm.
it's good enough. This one doesn't care. This one doesn't care
Just
with
looks
that
at the
composition.
vortex.
This one also has a pressure transducer and a temperature transducer, so it's a multivariable flow meter. It can indicate in volume or mass flow. That's like the bomb.
Let me be the devil's advocate here and say that I feel like different liquids would have different vortexes created by the same thing in the middle. Like, wouldn't a slurry have a different vortex than water?
Yeah, and we know the shedding frequency is a function of the velocity for that fluid.
So there's some calibration based on the density of the fluid.
Yeah, and we calibrate these with water, and you could tell us some of the properties like blood or oil.
Hopefully we
or-
don't have enough blood. Now we need a flow meter to,
Yeah.
you're bleeding and it's like, well, let's hook up the flow meter at 32 gallons a minute.
Yeah,
You got a problem.
it's done. People do it.
Okay, I'm gonna
Yeah.
pause this for a second and just make sure we're
And here comes Dave.